Okay, so this is a kind of a supplement to the last lecture. Last time we were talking about reconstruction of a cross-section of a human, for example, by parallel beam projection. And so it was like this was our patient, and then we had an X-ray source that moved in a parallel direction, and it was sending X-rays through the patient in this kind of a parallel beam geometry. And then these are being received by either a moving detector or an array of detectors. And so this was basically last time parallel beam reconstruction. And so what I want to talk about this time is what's called fan beam reconstruction. Beam, not beam. And the idea here is that instead of having a radiation source that is moving and parallel beams that are going through the patient this way, instead we have a fixed radiation source that kind of rotates around the patient. And in one configuration, this guy is sending out radial beams like this onto an array that may be flat or it may be curved. Or an alternate configuration is that, instead of having a single plate of detectors that rotates around the patient, instead the patient is kind of sitting inside a ring of detectors like this. This kind of looks like some sort of a creepy eye, but it's not. So each of these hash marks is like a detector, and then the X-ray source swivels around the patient, constantly shooting out rays and hitting certain detectors. And so, I think as I alluded to this time, this is what I would call a generation 1 CT scanning system, computed tomography. This is what you call something like generation 3, and this is what you call something like generation 4. And so, again, if you were to go to a hospital today, you would most likely be scanned with something like one of these detectors here. And I believe I have a better picture. So this is just a picture from the book of a better picture of the geometry that I just drew. And as I'll talk about it a little bit at the end of lecture, there are some modern CT scanners that are now actually even more complicated than this. And so I'll talk a little about that at the end of lecture. So the problem is that I can't just directly apply the equations from last time to this different geometry. And the reason is that instead of getting for each position or each angle a set of parallel beams, now I've got a set of angles this way, and at each place I have a kind of a fan, a spreading out fan of beams. And so we need different reconstruction equations, since the geometry is different. And so today's lecture is going to be basically a combination of changes of coordinates and trig identities and stuff like that. So it's a little bit tedious, but I just wanted to have it out here for completeness in terms of how things actually work. And so here's kind of our old sketch, right? So let's suppose that I have just one line through the patient. And so here's this one line, okay? Well, last time we talked about how I could describe that line with a distance, which we called rho, and an angle, which we called theta, right? And this was the fundamental rho theta that we used throughout the radon transform and the parallel beam reconstruction, okay? So now instead of rho theta, I'm going to start parametrizing this beam in a different way, okay, this ray. And so the idea here instead is going to be something like the following. So I'm going to imagine that this radiation source is fixed at a distance d. So this distance here is d, okay? And the source is going to be basically moving around the patient in a circle of radius d, okay? And now I'm going to define two new angles. And those angles are going to correspond to this same ray. I guess I can kind of color this in with a little bit of green to show which guy I'm talking about. Right, so here's a slightly different way of describing this ray, is by saying, okay, there's one angle that tells me how different this ray is from vertical. I'm going to call that angle beta. And there's another angle that says, you know, how far am I from the center line of the beam, which I'm going to call alpha. Right, so the idea is that as I rotate the source around the patient, that corresponds to changing beta. And then within a fixed beta, alpha tells me kind of where I am within the fan of beams that's going out radially, right? And so when alpha is 0, I'm along the center line of the beam, okay? And so the idea is that this here is like the, you know, center ray of, you know, the beta fan, okay? Okay, so we're going to use this change of coordinates, or we're going to use this coordinate system to say, okay, we used to be talking about rays that were defined in terms of rho comma theta. Now we're going to convert those to rays that are defined in terms of alpha and beta. Okay, so the idea is that each fan beam, which I'm going to call rho alpha beta. Actually, I guess rho is kind of bad notation for this because I used rho for this, so maybe we call it P alpha beta, corresponds to some parallel beam which I guess I can call the line going from rho theta, right? Okay, so the idea is to use a change of coordinates to go from rho comma theta to alpha comma beta. And before I go on, I'm just going to show a, you know, better picture of this. Again, this is right from the book. So again, you can see that beta indexes how far I am going around the circle from the source. Alpha indexes the kind of beamlet in that fan, and then rho theta is what I used to use. Okay. So, how do I know how to convert rho theta to beta alpha? Excuse me. So, it's kind of straightforward to see that this theta here is equal to beta plus alpha. Okay. So, this is true because here alpha in this picture is negative. Alpha would be positive going this way. So let me see if I can convince you why that's true. I had it on the tip of my fingertips before. So this basically says that beta minus alpha must correspond to this angle theta. I believe that's the same thing I'm saying. Right? That means that this would be theta. And that makes sense because if I call this angle here, this angle has got to be, you know, 90 minus theta. So, like, I've got a right angle here also, right? So, basically, hopefully that convinces you that this here has got to be the same as this here, and so on. Okay, so theta is equal to beta plus alpha, and my rho, I guess I made my diagram kind of messy, but remember this is a right angle here, right? And so I've got the hypotenuse, which is d, and that means that if I want to know what is the opposite, I should use the sign, right? So that means that alpha is, or that rho is d sine alpha. Okay. And so these two things are what I'm going to use in a couple slides to help me get to the reconstruction equation for the fan beam. Okay. So where did we end up with last time? So last time we ended with the equations for filtered back projection, right? We showed that this was the ideal thing that I should do to reconstruct the original image from its projections. And so here's where we got last time. This is saying that to reconstruct the original image, which I'm going to call fxy, so this is like the original image, I showed that I could get there with this equation. So I had, this was basically my radon transform. So this was basically the radon transform, the projection along the ray. And then I had this S that was like a window, and I was convolving these things together, right? So this here was a window function. And kind of putting it together, this is basically like a 1D spatial convolution with the window. And then the outer integral d theta is just like the equivalent of adding up all the rays as I go around the patient. Okay, so let me simplify this a little bit. So in practice, if I kind of look back at my geometry here, so here, remember that rho was like this distance, right? And so in this case, rho is definitely going to be bounded, right? It's not going to go from minus infinity to infinity because the patient is only a certain width, right? So that means that I can kind of say that there's some maximum rho. So I can change this integral from minus t to t. That's going to be like my boundaries for how big rho could possibly get. And then in terms of theta, you know, the reason that I only did 0 to pi on theta is because if I flipped theta around by pi, I'd be getting the same rays going the other way in just the same integrals. That's why, to make it simpler, last time I just said 0 to pi, but in this case I'm going to add a 1/2 here and go from 0 to 2 pi. I should get the same answer. Okay. So now what I want to do is I want to go from my xy world to polar coordinates. Okay, so remember, xy is some point in the original image, and instead of calling it Cartesian, I want to call it polar. So, so now I'm going to convert xy in Cartesian to, let's call it r phi in polar. And remember, what is this xy? This xy is like a fixed pixel in the original image. So instead of calling that pixel by Cartesian coordinates, I'm going to call it by polar coordinates. Okay. So for that, I need to do a substitution. And so I know that this is the way that polar coordinates works. X is r cosine phi. Y is r sine phi. I'm using phi here because there's a theta elsewhere that I need to keep straight. So it's just a reminder that if this point here is x comma y, then this is r and this is phi. Okay. Okay. So let's plug in what we get. So that means that inside my integral, I have x cosine theta plus y sine theta minus rho. And so I'm going to have x cosine theta plus y sine theta appears inside that integral. And now I'm going to substitute what I know. This is the same thing as r cosine phi cosine theta plus r sine phi sine theta. And by trig identity, I can recognize that this is the same as r cosine of the difference, theta minus phi, right? So here, I'm kind of using trig identities, which I'm going to just write down here for my own reference. So if I have the sum of two angles, I have this thing. And if I have the sum of, or the difference of two angles in the sine, I have this thing. So what I did is I recognized that this thing here, the top one, looks like this, except I've got a minus sign instead of a plus sign. So it's kind of like this. Okay. So now I'm going to plug in what I just figured out. So I'm going to go back to this and substitute in my polar coordinates. So what I have is, now I've got an r comma phi on the left, because I'm now parameterizing my reconstructed image like that. I've got a 1/2 integral from 0 to 2 pi, integral from minus t to t. This is my radon transform. This is my window function, which now has things that involve r and phi instead of x and y. And I noticed that there was a typo in Gonzalez and Woods, at least the edition that I had, so be careful if you're following along with the book. Okay, so now the next step is to say, okay, well, I don't really care about rhos and thetas, right? I don't really care about parallel projections. What I care about are these new fan beam projections. So I want to turn every rho theta ray into a alpha beta ray, and I'm going to use my equations to do it, right? So let me just write down as a reminder that this is my relationship between my old parameters and my new parameters. So if I'm going to do a change of coordinates, that means that I need to know what does d rho d theta correspond to in terms of d alpha d beta. Well, I need to do this absolute value of the determinant of this matrix where I've got, so d theta d alpha is 1, d theta d beta is 1, d rho d alpha is d cosine alpha, d rho d beta is 0. Right, so this is just the Jacobian. And if I do the determinant, what I get is d cosine alpha, d alpha, d beta. Okay, so now I'm going to change this whole integral here from a rho theta integral to an alpha beta integral. Okay, so my integral becomes, well, if theta is ranging, so I'm going to put the, let me think about this. I'm going to put the alpha integral first. So the alpha integral is going to go from, well, it's related to rho, right? So that means that alpha is rho over d sine inverse, right? And so if my rho is originally ranging from minus t to plus t, that means my alpha is going to range from sine inverse of minus sine inverse of t over d to plus sine inverse of t over d. My theta is going around from 0 to 2 pi. Since alpha is on the outside, that means that my beta, alpha is going to be fixed. That means my beta is going to range from minus alpha to 2 pi minus alpha. Then my g of rho theta becomes, I should have left myself some room here. My g of rho theta becomes, well, rho is d sine alpha. Theta is alpha plus beta. Then I have my windowing function, which is just coming along for the ride here. Except now my theta is going to be alpha plus beta minus phi. And my rho is going to be d sine alpha. Then I have a extra d cosine alpha from the Jacobian. Kind of a mess. So let me make this a little bit simpler. So what I'm going to do is I'm going to say, okay, I'm going to call this thing, which is basically, the integral, the radon transform along this ray. I'm going to give this a new name. Okay, so I'm going to call that P, which I think I already did on a previous page. So I'm going to call that, so a couple things I'm going to do. First, I'm going to say, let's make this easier and just say that I'm going to give these guys a name, which is like the maximum alpha, right? So instead of carrying this crap around, I'm just going to say that this is the range of the alphas in the fan. Here, since everything is 2 pi periodic, I don't really have to worry about this alpha inside here. I can just turn this into a 0 to 2 pi because I'm going around the circle either way. I'm going to call this thing P of alpha comma beta. That's like the integral for this fan beam. And then I'm going to have this windowing function. then I have my d cosine alpha, d beta, d alpha. Okay. And just like a minor note is that I always find that it's better to, like I have this kind of convention where this is the inner integral, d beta, this is the outer integral, d alpha, right? Sometimes you'll see a book that will switch these guys as if you kind of already know which integral corresponds to which d. I find that can be a little bit ambiguous sometimes, so here I just want to make sure that you know that this is the inner integral, this is the outer integral. Okay, so now I'm going to try and simplify this further, and the biggest culprit right here is this kind of crap right here. Okay, so now I'm going to make my life a little bit easier, but I need to draw another kind of confusing diagram. Okay, so let me put this aside for a second and draw a picture again. So what we were doing before is we were considering a certain point xy. That was the point in space, and we also were saying that we're actually in the fan beam world talking about that in terms of r and phi. Okay. So now I'm going to do the following. I'm going to draw a ray. So I'm going to say, okay, I'm working in the beta world. Okay, so let's suppose that this is my I'm worried that I drew this ray a little bit too, well, this will be okay. A little bit sketchy, but okay. So this is my ray that has angle beta, right? So this is like saying, where is xy with respect to the beta-th ray? So the alpha that corresponds to that xy is going to be, let's call it alpha prime, okay? So here, this is kind of like saying, okay, well, what is the alpha prime that corresponds to, you know, which of the fan beams goes through xy if beta is fixed? So I'm going to kind of remind myself. I'm going to call this distance here r, capital R, the distance between these two dots. And then I'm going to draw this perpendicular here, like so. Now again, from kind of same angles, I can convince myself that this angle here has to be beta. And I think that's easy to see, but I'm trying to figure out what the easiest way to show it to you right now is. Let's think about this. So that means that this angle has to be beta. Yeah, I think you can see it from here, right? So that means that by this angle is also beta. And here I think that's why this is true, right? Because here this is just a right angle picture of this triangle. So these two triangles are basically flipped around for each other. Okay, so that means that this angle here, so that means this angle here has to be 180 minus phi, right? If I kind of draw this like this, that means that this angle here has to be beta minus phi, right? Because these angles of this triangle have to add up to 180, and beta plus this angle has to also equal 180, right? So this angle here is beta minus phi. Okay, a little bit tedious, probably a lot tedious, but where does this get us? Okay, so what I was trying to do was make one of these integrals easier. Now I'm going to think about, okay, well, let's consider this distance. I'm just going to put a circle 1, right? So there are two ways of describing this distance, right? One is based on, well, if I think about this little r as a hypotenuse, I can think about this as the adjacent to the hypotenuse, where the angle is r cosine of beta minus phi. Or I could think about it as the hypotenuse of a, here's a bigger hypotenuse triangle, capital R, and this angle is alpha prime. So I could think about this as the opposite, where this is r sine alpha prime. Those two things are the same. And Now I'm going to make another guy here. So this distance here, I'm going to label number 2. Okay. So again, I can think about this in two ways. One is this is the opposite angle here. So this is like little r sine beta minus phi. Or I can think about it as the adjacent to this, where I've got, well, actually, I know that this thing here is just, so D, I guess I should be a little bit clear. So D is going up just to here, right? So this thing here is actually this distance, which is the r sine beta minus phi, plus this other distance. That's what gets me to this whole thing, which is then r cosine of alpha prime. The reason I'm doing this is that it will make my life a little bit easier in just a second. Why is that? Well, what have I got over here? Going back to what I was originally trying to simplify. Well, let's think about this. This thing here on the inside is r cosine alpha plus beta minus phi minus d sine alpha. I'm going to apply my cosine sum rule, right, which says that this is going to be r cosine of beta minus phi cosine alpha minus r sine beta minus phi sine alpha, and then I have this d sine alpha, which is a different way of saying r cosine beta minus phi cosine alpha minus r sine beta minus phi plus d sine alpha. Well, why did I do this? Well, now I observe that these things that I got here are exactly what I just derived. So if I move this down a little bit, here I see that this part here is like capital R sine alpha prime cosine alpha minus this part here is exactly R cosine alpha prime sine alpha. That's why I did this whole schlep in the first place. And now I observe even further that this is actually like R sine of alpha prime minus alpha, right? This is just from the trig sum formula. Okay, so now I've made my interior integral a lot easier. So here, the thing to observe is that, you know, R and alpha are both functions of r comma phi, which is the point in the image I'm trying to reconstruct, as well as beta, which was the particular angle that I was thinking about xy with reference to, right? So as I rotate around different betas, I'm going to get different capital R's and different alpha primes corresponding to the same point. Okay, so now I can make my life nominally easier by saying that this thing will become S of capital R sine alpha prime minus alpha. And then I still have this d cosine alpha floating around here. Okay, so I've made this my life a little bit easier with this. Okay, one more simplification. So now I have this thing inside the integral. And let's remember where this thing came from in the first place. So remember, this S was defined as the inverse Fourier transform of the window function. The window function was basically the absolute value of omega, right? So we kind of showed last time that what I needed to do for filtered back projection in the frequency domain was to apply this filter, right? So the idea was that the filter in filtered back projection is exactly this guy here, right? That's why I need to multiply each of my projections by, because we remember we talked about how the middle was sampled much more often than the exterior, and so this is the function that undoes that problem, right? And so now what I have in my equation here is I have an S of r sine alpha prime minus alpha. So what I have is this. And let me just for a moment call that some other number gamma. Okay, so this is kind of what I'm faced with dealing with. If I plug in what I have e to the j 2 pi. I'm evaluating this at t equals r sine gamma d omega. And now I'm going to make a change of coordinates here to make my life a little bit easier. I'm going to call this thing now call omega prime equals omega r sine gamma over gamma. Okay, so this is kind of a weird change, but you'll see why it's useful in just a second. So that means that my d omega prime is going to be basically r sine gamma over gamma d omega. And that means that if I plug in things for omega prime, it sounds like a transformer. Sorry. So that means here, this is like saying S of r sine gamma is equal to, well, if omega is ranging from minus infinity to infinity, so is omega prime. Now this is going to become omega prime, but I'm going to have an extra one of these guys to take out, so I'm going to have a, let's see, I'm going to have a gamma over r sine gamma, and then I'm going to have another one of these guys from the d omega prime, right? So omega prime times gamma is the same omega r sine gamma I have in the numerator here. Okay, so I'm just going to kind of move this guy out of here like this. And then if I do that, I notice that this actually here is just the same as evaluating the window function at gamma in the first place. So what I did here is I kind of made it easier. Instead of having an r sine gamma inside here, I was able to kind of sneak it out of the integral. Okay. So now when I put this all together, so putting it all together, I arrive at the following thing. So this is where I started. This is like saying I want to reconstruct the signal at this point. Okay. Then I have my beta integral going from 0 to 2 pi. And then I have, I'm going to make my life a little bit easier by a couple of simplifications, which I'm going to say in just a second. So what do I do here? I defined this H is something that collects some of these terms that were hanging around before. I defined this Q as something that is basically like the alpha beta projection, but I'm going to fold in the d cosine alpha term here, right? So the idea is that this inner integral here, so this guy here, is just a convolution of the projection for a fixed beta and a window function h. Right? So this is just kind of like a different kind of filtered back projection. And then this outside thing basically says sum up these back projections as I go all the way around the circle, right? So this is just a kind of a different way of thinking about filtered back projection, right? So these are my projections. I modify them a little bit with this cosine alpha term. And then here you interpret this as a convolution where fundamentally alpha here is like the dummy variable of the convolution. Beta is fixed inside here. And this alpha prime kind of corresponds to what, what am I doing over here, right? And there's also like an extra factor of r squared in front of the integration term. So, this is like pretty tedious, hard to imagine that you'll ever need to use it in real life, but it is, the answer to how these fan beam projections work. And so I didn't want to kind of leave the topic without talking about the details. So this is kind of like the key equation for fan beam reconstruction. Okay. So last thing I want to say on this topic is that there is a less accurate, but computationally a lot more straightforward way of doing a fan beam. So a less accurate, but much easier way of dealing with fan beam projections is the following. So what do I get when I do fan beam projections? So I've got the patient, which I'm going to actually, I guess I'm just going to kind of ignore the patient here to make life easier. So here I am at one point on the circle, and I send out my fan beams. Now I move to, and I guess I should probably just draw in the circle to make my life a little bit easier here. Now I move to a different point in the circle, and I draw some more fan beams. And my drawing gets immediately more complicated. And then I move to a different point of the circle, and so on. I draw some more fan beams. So the thing that you can notice is that actually, some of these fan beams can kind of be resorted to produce parallel beams, right? So the idea is that I could notice and say, hey, actually, this beam here from this direction, and this beam here, although I didn't draw it very well, from this direction, and this beam here from this direction, kind of form up some parallel beams, right? So the idea is, well, why don't I take all the fan beams I got and resort different beams from different values of beta to kind of mimic what I would have gotten had I gotten parallel beams. And then I use my parallel beam reconstruction formula, which is, easier than the fan beam one, and then just go from there. So the kind of idea is to resort fan beams from different beta into collections of parallel beams. Which is a kind of a clever idea. And so mathematically, what does that mean? So kind of mathematically what that means is it's like saying that, well, my alpha comma beta fan beam corresponds to some, my alpha comma beta fan beam corresponds to some rho comma theta parallel beam. And the rho comma theta that I have is basically from a previous change of coordinates, right? This is how rho, theta, and alpha beta are related. So this tells me which fan beam corresponds to which parallel beam. And if the fan beams are equally spaced, so suppose that I have some really fine spacing of fan beams where my delta alpha and my delta beta is some angle gamma, then that's like saying that, alpha corresponds to some multiple of gamma, beta corresponds to some other multiple of gamma, and then this here corresponds to sine of n gamma, and this corresponds to n plus m gamma. So this is like saying that the nth ray in the mth radial projection is the same as the nth ray in the m plus nth parallel projection. And so this makes it really explicit about how do I choose beams from here to produce beams from there. The problem with this whole approach is that, if I go back to this picture, even if I'm equally spacing, alpha and beta, there's no guarantee that the rows that I have, right, which are basically the distances between these lines, are going to be uniformly spaced. So, what I'm saying is that rho is not uniformly spaced in this kind of increment gamma, and so we need to do some interpolation to get all the values of rho that we need. Because if you think back to the discretized version of the parallel beam reconstruction, we kind of need to have this finely spaced set of rho that are equal. But this is really not an issue if gamma is small enough. You just need to choose gamma to be small enough that you don't have any sort of aliasing artifacts, because then you go back to this kind of sampling theorem argument that says that if I don't sample finely enough, then I can't do ideal reconstruction of the underlying signal, right? So this is kind of like a Nyquist argument about how fast or how small those gamma need to be so that the interpolation that I do is the ideal thing I would have gotten. So I'm not going to show you really anything too much in Matlab, other than to say that Matlab does provide you with the commands to go back and forth with this exact kind of resampling and interpolation. There are commands called para to fan and fan to para, and then there are direct commands for fan beam and inverse fan beam. Right, so these are the commands that are really relevant to us here. And if I do, doc fan beam, this is kind of like the equivalent of the original radon transform. So here, this is particularly for the fan beam reconstruction, and I have to specify what is the radius d, what is the maximum thing. So the fan beam commands have like a ton of extra involvements, and certainly if I want to convert fan to parallel and so on, then there's like a zillion little details about the geometry and the sensor spacing and what kind of interpolation you use and how much parallel sampling you want. So you can just basically run these things to see how a fan beam works. I mean, I'm not going to show you too many images because the reconstructed images look a lot like parallel beam reconstructed images, so you're not really going to see anything too different. So the last thing I wanted to say is that if you're getting treated for cancer in a really modern hospital, then you may have even more interesting geometries, right? So here's a kind of a helical CT scanner, where instead of taking slices of the patient like one slice at a time, which is kind of what we've been talking about so far, where you imagine that as the gantry, as the patient moves through the gantry, we're basically getting enough angular samples of the patient each moment in time. Instead, you could have an X-ray detector that is rotating around while the patient is being smoothly moved back and forth on the couch. That means that you never have to discretely kind of chuck the patient into different increments. Instead, you're smoothly moving the patient and smoothly moving the X-ray. This is called helical CT. And then even more modern is something called cone beam CT, which is basically instead of getting one slice through the patient, this is like a fan beam geometry. Instead of getting one slice per patient, you instead have an aperture that lets a kind of a cone of angles through the patient. And then instead of having a one-dimensional detector, you have a two-dimensional detector, right? So now, as at every angle, you are getting a image that is like a projection. Then I need to reconstruct the 3D geometry of the patient from a whole bunch of these images. So as you can imagine, the mathematics for that is even worse than what you just saw here. But the fundamental kind of ideas apply. So, this, I think you would call this like a generation 7 CAT scanner is probably a cone beam. And certainly a lot of my colleagues in medical physics are using cone beam CTs in their research. So, okay, so that's it for parallel projection, or I'm sorry, that's it for reconstruction from projections. I think the most important thing to really understand is the radon transform, but hopefully you got something out of understanding the complications of this other geometry. Okay, see you next time.